Good evening, everybody. Thanks, Hollis and Sean and the whole gang over at the online meeting group of ASHI. Happy to be here to talk to you guys about some combustion safety basics. You know, what I say basics may be a little bit advanced for some. It may be rudimentary for others. The area or when I became a home inspector, very soon after that, I came across BPI, Building Performance Institute training. That field of study, that certification delves into diagnostic testing of homes. Obviously, when we're doing a pre-purchase home inspection, it's a visual inspection of the individual systems. We're not looking at system interactions. But at the time I got into the business, sales of homes were down. People were spending money on renovating their homes, and there was money there for energy efficiency upgrades. And the BPI certification was the certification of choice for weatherization and other programs that were incentivizing people to make their homes more energy efficient in a safe and effective manner. And the combustion safety testing processes that I mention or allude to are generally brought to my attention by BPI. It was a little bit frustrating to see problems in homes and ask people what was the cause of it. And sometimes you'd ask HVAC guys or plumbers or professionals that you would expect to be able to give you a clear answer, and they couldn't. And it wasn't until I went through BPI training that it kind of tied all those systems together for me. And as we make homes more airtight, less drafty, more comfortable, more energy efficient, combustion safety you start bumping up against combustion safety. Combustion safety likes leaky, drafty homes, but we need as how homes are getting tighter because people are doing weatherization work to them, we're going to start seeing combustion safety issues. So. And by the way, this is one of the differentiating factors that we use in our business, like Mike was mentioning. How do you separate yourself from other folks, from other home inspectors? Well, sure, we do home inspections, but we're building consultants, which means anytime you have a question about a building, whether you're buying it, selling it, building it new, or renovating existing, they know to give us an insider call. So I always ask people, how many of you are home inspectors? How many of you are building consultants? Because I can do business with every homeowner if I'm a building consultant. If I'm a home inspector, I'm waiting for something to sell. So consider that as we go along. Hey, Hollis or Sean, how much time have we got here? Just want to be sure.
You have till 9:30.
Oh, okay. So we got an hour. Okay. All right. All right, just want to keep track right. Okay. So why combustion safety? Because we use hydrocarbon fuels to heat our homes, and those are hazardous. They can result in explosions or fires. Less drastically, we can have poor indoor air quality because of these hydrocarbon fuels. The exhaust byproducts that are generated are harmful or deadly. Safe and efficient combustion is desired by all, right? We don't want the fire or the exhaust byproducts getting out of their intended location, and we want to make sure that none of that stuff's creeping into our bedrooms. We need to have proper exhaust management. Also, we need to be aware that fires often happen thoughtlessly. Just people are not quite paying attention to what they should. If you sometimes stop and ask them, they'll realize their foolish, or absent-minded placement of a stack of newspapers in front of a water heater, right? Oh, there's fire under there. Oh, okay. Well, maybe I shouldn't put put paper by the fire. So sometimes we have to, I think everybody here will agree, we do a lot of educating of the folks that we inspect homes for. So, and that's not going to stop. We're going to keep educating them as we go. So our clients do want a safe and healthy home, and when we do home inspections, they you know, that's part of what they're expecting us to find is issues that are unsafe or potentially unhealthy. I know unhealthy kind of gets into a gray area, but you know, it's something that we need to be aware of. And if something is brought to your attention or you notice something, it can't do anything but help you to alert the homeowner to a potentially unsafe or unhealthy issue in the home. And you have to be able to communicate the level of risk that's involved in the required action. There's people, I characterize people as the canaries and the billy goats. And the canaries are sensitive to everything, right? And those are very challenging clients to deal with. Then you have the billy goats that don't care, man. They don't care if there's radon. They don't care if there's exhaust spillage. They don't turn on range hoods over their stoves. They don't care. They're billy goats. So when if you're dealing with if you're dealing with that canary, well, then you're going to be doing a lot more of this, communicating levels of risk and required actions. If you're dealing with billy goats, it's probably going to be a pretty short conversation because they're just not going to care, but you're still going to write it up because you've noticed it and you got to cover your own behind. All right, so today what we're going to be talking about is ambient breathing zone carbon monoxide. We're going to talk about fuel, gas leaks, combustion air for our gas combustion appliances, the CO production that is part and parcel to all gas appliances. We're going to talk about exhaust spillage signs and some of the dynamics that can lead to exhaust spillage. We're going to talk a little bit about dryer safety. All right. So here's our combustion process. We have CH4. There's your hydrocarbon. It reacts with oxygen. Pow, we got energy. And we have the byproducts of water and carbon dioxide, right? So part of the reason why we don't want to exhaust into the house is we're going to be dumping a lot of water into the house. I believe it's a gallon of water is generated when you burn 100,000 BTU of 100,000 BTU worth of gas, right? So it's a lot of humidity in the air, and we need to get that out of the house, along with the carbon dioxide. But unfortunately, combustion is rarely perfect, and we have other byproducts that result from incomplete combustion. Now, that CO production can be the result of inadequate combustion air. Sometimes it's high gas pressure. If anybody has the ability to measure carbon monoxide on a gas appliance and you're looking at the CO output, you normally see a spike at the beginning, but usually as the system heats up, the CO drops. If it continues to build throughout the firing sequence through 3, 5, 6 minutes, and it's going up and up and up, generally it's a sign of the gas pressure on the gas control is too high. It's just feeding too much gas. You can't burn it up. No matter how much combustion air it's got, it's just being fed too much gas, and you're going to start seeing carbon monoxide levels build. Obviously, everybody knows to look for dirty or misaligned burners. We're trying to find that nice clean blue flame. We don't want to see the yellow, orange, looking flames that leave, soot all over the place. We want a nice clean white, whitish blue flame. Flame impingement is another thing that can create CO production. That is whenever the flame is touching metal, right? Something is impinging the flame. If you put a pot on a burner on the stove, you've got flame impingement, right? So it's right there. You're cooling down the reaction. You're creating more carbon monoxide as that flame is impinged. So you can't help but create carbon monoxide when you're cooking on a gas stovetop. Then we have backdrafting of combustion byproducts, and those combustion byproducts again are the carbon dioxide that is going. Even with perfect combustion, we're going to have carbon dioxide. Imperfect combustion, we have carbon monoxide, and then we have other acidic gases, right? They're referred to as NOx and SOx, nitrogen oxides, sulfur oxides. Those are the gases that will tickle your sinuses when some gas appliance is burning and the exhaust is filling the home, right? You're not going to smell water vapor. You're not going to smell carbon dioxide. You're not going to smell carbon monoxide, but you will smell the acidic byproducts of nitrogen oxides and sulfur oxides that kind of irritate your sinuses. And that'll let you know that, hey, there's some, maybe you were testing the oven, you forgot to turn it off. Usually that smell will alert you to the fact that you maybe left something going. They also, part of the nitrogen oxide and sulfur oxide is also the result of the mercaptan that's put in natural gas to give it that rotten egg smell so that we can detect leaks, right? So as that burns in the combustion process, we get some of those acidic byproducts, right? So, and if any of that is getting drawn back into the combustion process, well, then even more of those acids and byproducts get created, and it gets bad fast. It starts basically breathing its own combustion byproducts. So regarding carbon monoxide and carbon monoxide alarms, the UL alarms that we see, the 2034 alarms that we have in homes are not very sensitive, right? You can see that, at low levels, we can, you can see symptoms of carbon monoxide poisoning in kids, the elderly, the unwell, at relatively low levels, 10 to 35 parts per million. A UL 2034 carbon monoxide detector will only go off if we've got 70 parts per million for 30 days, right? Somebody opens up the door, it goes down to 68, the counter resets, and you've got to hold that 70 parts per million for 30 days. Now, if it gets up to 150 parts per million, it cannot go off in less than 60 minutes, but it has to go off within 240. If we're at 400 parts per million, it cannot go off before 10 minutes, must go off before 49 minutes, and if we're above 400 parts per million, it cannot go off in less than 4 minutes, but has to go off within 15 minutes. So you start looking at these, if a carbon monoxide detector is going off, you either have had a low level, not even really all that low, a moderately high level of carbon monoxide for an extended period of time, or you've got a dramatically high carbon monoxide concentration in the house for a relatively short amount of time. Either way, when a carbon monoxide detector goes off, it's not because it's super sensitive. It's going off because you have a life-threatening situation in the place and needs to be taken seriously. I think carbon monoxide detectors are often ignored because of all the false positives we've had from smoke detectors. Oh, I burned popcorn, I burned toast, whatever, right? And so people think, they disregard the smoke detectors. If a carbon monoxide detector goes off, you've got a serious issue. You got to start paying attention, and I try to get that into the head of all my homeowners. There's no such thing as a super sensitive carbon monoxide alarm that you're going to find at a big box store. They don't sell them. Now, you can buy something like this from CO Experts. These are low-level carbon monoxide detectors that a consumer can put in their house. And again, if you have somebody who's sick, who is immune compromised, who's old, or very young, low body mass, poor immune system, already dealing with health issues, carbon monoxide robs your body of oxygen at a cellular level, right? Your body's not going to be able to deal well with that. And if you're already compromised because of other comorbidities or issues, the carbon monoxide is going to really hurt those folks. So my opinion is to place carbon monoxide detectors near the source of carbon monoxide. If it's going off all the time, you've got problems all the time, right? This is not something that will just go off because it happens to be spilling a little bit of exhaust at the water heater. I've had water heaters in one of my rental properties. The water heater was spilling exhaust for an extended period of time. The only reason I knew about it is because people were complaining about their runny nose and their sore throat because of the exhaust byproducts in the house. When I checked the carbon monoxide detector that I placed right above the water heater, the highest the CO got was 12 parts per million, right? So you can have a gas appliance spill exhaust into the house, not guaranteed that the carbon monoxide detector is going to go off. It'll only go off if it spills and the carbon monoxide levels are high, right? So the one I had said peak level 12 parts per million. That'll never go off. It'll never go off. So, but if we do have high levels, I do want to position it near the source, and we're looking at, the furnace, water heater, the stove, the dryer, fireplace, and the attached garage, because we've got carbon monoxide sources out in the attached garage. All right. Carbon monoxide detectors, about 3 to 5 year is a typical sensor life. I saw one yesterday that was 25 years old. That one's no good. The sensors wear out. The test button is for the battery, not the sensor. So if it screams when I hit test, it's only because there's enough juice in the battery. It's not a test of the sensor. Newer sealed carbon monoxide detector units claim a 10-year service. We were at a tour of UL labs here that certify carbon monoxide detectors, and they assured me that the newer units, if they say they're good for 10 years, they're good for 10 years. So obviously the devil's in the details there, and we very often don't have any kind of paperwork that says, you know, what the life of a particular carbon monoxide detector is. But again, the older units, units that are more than 5 years old are not going to have the 10-year lifespan. If they have sealed battery, chances are they've got the longer life. So something to be aware of. When I'm going through a home, I'm generally monitoring ambient carbon monoxide with this personal carbon monoxide detector. From the time of entry, we're looking, anything above 9 parts per million is going to, make my spidey senses tingle, and I'm going to start looking for the source. I'm going to ventilate the house. We've gone into homes where it's 30 parts per million walking in because somebody had left the burner on the stove on simmer all night long. Could barely see the flame on that thing. But with this unit, as I walked through the house, as I got closer and closer to the source, the concentration got higher and higher. And we were able to identify source of it, shut it down, ventilate the house, make it safe for people to be inside. Now, we're going to go over to detecting gas leaks. So I know most folks here have got some type of combustible gas detector. Whether you've got fuel oil in your market, propane, natural gas, if you've got those fuels in your marketplace, you're likely doing some type of gas leak detection on the fuel delivery system. Keep in mind that these units typically need to be zeroed out outside. Some of them say they don't need to be, but it's always safest to zero them out outside. If they wake up in a 0 part per million environment, then anything that they detect they'll be more sensitive if there's elevated levels inside the house. You want to have one that can adjust the sensitivity. You want to slowly move the sensor around the joints. We want to check all accessible fuel pipes and joints. We are not moving appliances, right? I don't move stoves. I don't move dryers. The only way I'm moving an appliance is if I've got the parts to fix it. And I don't generally carry spare gas lines with me. So I do not move appliances when I'm doing this. But knowing that natural gas rises, I can put my gas sniffer behind the dryer, and if it pings on me, then I know I've got a natural gas leak somewhere behind the dryer and the natural gas is rising up. Conversely, if I've got a propane house, I know that propane's heavy, it's going to fall. I'm going to be sniffing along the floor in front of the dryer or the stove or whatnot. There's a leak back there, it's going to hit the floor, it's going to come creeping out through the front. Sometimes you can figure out exactly where it's leaking, and sometimes you just know that there's a leak in the area. Either way is useful to our clients. We're reporting gas leaks. I generally want to confirm the leak with soap bubbles. You can see a little graphic on the top left, little bubbles forming at that union there. Typically, we'll tag it like you can see at the bottom left. Take a photo of that. It's real easy to communicate that in the report. We generally will leave a notice for the homeowner. Again, on a pre-purchase home inspection, I'm testing it for somebody who doesn't own the house yet. Then the homeowner finds out, maybe a week later, if they see a copy of the inspection report that or they get it in a request from the buyer. Oh, by the way, we need you to fix the 3 gas leaks that were detected. Homeowners lose their mind. So we actually have a little safety form. Any kind of safety issues that we notice in the house during our inspections, we'll leave a safety form for the homeowner. So when they return after the inspection, they can see that we found gas leaks or whatever the case might be. Also, these pre-1973 brass gas lines. Again, I'm not moving the appliance, but if I peek back there and I see an old uncoated brass gas line, that thing is as old as me. right? Gas lines ought to be changed out with the appliances. So what, every 10 to 20 years, right? So if there's a brass gas line, that thing should have been probably changed out 3 times already. So do not move them. Material fatigue is going to let go at some point, and you don't want to be the one that moves it, and that's when the pipe cracks open and starts, leaking gas. So we have some older coated brass lines, and then we have some uncoated stainless steel. Again, those are newer, not as big a concern, but again, usually I'm putting the gas leak detector back there to see if any of those are leaking, but the old brass ones I know haven't been changed out in quite some time. Gas leaks are the most common issue that we see in homes. Typically, I generally catch about 1 per house on average. That average lately has been diminishing, right? So I'll go on long stretches where I can't find any gas leaks. But when I started at like 5 years ago, I was finding 1 per house. So I'm still looking for them. Maybe my colleagues are getting better at finding gas leaks. The HVAC contractors are getting better at sealing up their work when they replace furnaces. Plumbers are doing a good job with the water heaters. But again, for a good long while, I was finding, it was typical for me to find at least 1 gas leak per house. And again, I tell homeowners, it's not normal, right? It's not acceptable, but it is typical, sadly. So keep an eye out for gas leaks. Again, some of these symptoms, when we do energy audits for folks, one of the things that we look for before we tighten up people's homes is to see if there's anything that's going to be an issue if the house sees less fresh air exchange. A gas leak is going to be one of those things. People will often report respiratory or allergic reaction type symptoms. Their mold allergies are kicking in, or they go to the doctor and the doctor's saying they have respiratory sensitivities. This can all be from low-level gas leaks. Small enough that there's no explosion risk, nobody's walking in the house and smelling a gas leak, but the canaries among us will start to have respiratory reactions to that. And it could be from an a yet unidentified gas leak. So keep some of these things in mind. It might, you might be the hero that finds the problem for somebody that nobody else has been able to find. So gas leaks and exhaust spillage can lead to those undetermined causes of respiratory issues or sinus issues. Okay, now getting into combustion air for our gas appliances. When we had big open basements and there's a furnace down there, combustion air wasn't a big problem. When somebody starts to constrain that space by finishing the basement, now we've got a smaller box around our furnace or water heater or whatnot, and we got to make sure that there's enough combustion air or enough volume of air for combustion for that furnace. So the standard is we need to have 50 cubic feet for every 1,000 BTU per hour capacity of furnace. So if we have a 100,000 BTU furnace, then we need to have 5,000 cubic feet around that furnace. For an 8-foot tall ceiling, which is pretty standard, we need to have a 625 square foot space around that furnace. Again, in a basement, probably not a big deal, but if we're putting furnaces in the closets or we're finishing the space around it and basically building a closet around it, this can be an issue. And I just ran the numbers again for 60,000 BTU furnace. The equation's the same, but that can be in a little bit of a smaller space. Now, this is if all of the air combustion air is supposed to be coming from inside the home. If that is deficient, then we can bring in combustion air from the outside. The ideal scenario would be a 2-opening system. They could be horizontally ducted through the side, or the other kind of classification is that they could be 2 openings that go directly outside, or 2 openings that are vertical to the attic, vertical up through the roof. Now, the horizontal duct, because the air is moving through a constrained opening horizontally, the standard there is 1 square inch of opening for every 2,000 BTUs per hour of furnace capacity. That's each opening. When we look at the other classifications, the direct to outside or the vertical configurations, they need 1 square inch of opening for every 4,000 BTUs. So if we have a 100,000 BTU furnace in each one of these spaces, you can see that the horizontal ducting strategy is going to require that we have a total of 100 square inches of opening to the outside, whereas the direct to outside or the vertical duct configurations only need 50 square inches total. All right. These openings through the walls have to be within 12 inches of the ceiling and 12 inches of the floor. All right. So the opening of the pipes, again, within 12 inches of the ceiling and floor. The other option is to do a single opening to the outside, and this unit or this scenario requires 2 square inches of opening for every 3,000 BTUs per hour. So again, that 100,000 BTU furnace is going to require an opening that's about 67 square inches. All right. Again, opening must be within 12 inches of the ceiling in this case. So we're not putting that combustion air opening near the floor. Code wants it up within 12 inches of the ceiling. Now, if we have these openings need to be closed off to some degree for pests. So we want to see a 1/4 inch screen on those. And if that's all it is, it's 1/4 inch screen, we don't have to derate it for net free vent area. But if there's any louvers in front of these openings, we have to derate it. So that opening, we only can count 75% of it if it's got a metal louver. We only get to count 25% of the opening for wood louvers. So if we got an opening with wood louvers, it needs to be 4 times the area than just a screened opening, right? So the short answer would be get rid of the wood louver and put a metal louver on there, and you've made up a heck of a lot of ground. So I don't know how many people are doing these calculations on site. I very rarely come across a scenario where I'm calculating combustion air from the outside. Generally, we're looking at, are there openings? Are they positioned right? Did somebody cap them off since they've been installed? That's pretty typical, that somebody decides they just want to close it off because they don't need it anymore. If the gas appliances are using room air for combustion, then this is something that we need to be concerned about and keep an eye on, making sure that the units have enough combustion air.
Hey, Joe.
Okay. Yes, sir.
Why are there 2 openings instead of 1 for combustion air?
The idea is that we want to have one for combustion air and the other one for draft air, and to allow any spilling exhaust to escape, to allow any spilling fumes to escape. So generally the idea is that if I have exhaust spillage, that exhaust is going to rise up, and those openings near the top will allow that to escape. But because our combustion is near the bottom, we want to have a fresh air source near the bottom. So when they developed the code or these requirements, they wanted openings high and low, one to let air in, one to ostensibly let the bad stuff out. Now, unfortunately, air doesn't always follow the wonderful little arrows we write down on pieces of paper, but having 2 openings, again, it's perceived as being a safer setup, and the combustion air can get in more freely, and fumes can get out. So hope that answers it. Any other questions there?
Nope, that's it. Thank you.
Okay. All right, we'll plug along here. So gas oven testing. You can, obviously there's a combustion analyzer in that image there where, we're actually putting the probe right into the exhaust port of the oven there. So the oven exhausts right, usually in that backsplash. That's why the top of the oven gets nice and toasty when you're running the oven. So we're generally, measuring carbon monoxide, as it just before it comes out of that opening. When we're doing this, typically we're opening a window, we're turning on the exhaust fan, presuming the exhaust fan actually exhausts outside. If it's a recycler, it's just making noise, and I don't think it's not going to help you as far as minimizing your exposure to exhaust gases. Again, we're testing the CO level in the undiluted stream of exhaust. The oven is generally set at the highest setting, so we set it to like a broil, high, and let it roll for up until steady state. We also want to monitor our ambient CO while we're doing this. So that the little ambient CO detector, that rattler, I usually have that clipped to my shirt or put on a lanyard or something around my neck. My breathing zone is around my face. It's not at my hip. It's not on my belt. So when we're doing these tests, you want to make sure that carbon monoxide detector is there to keep you safe, keep you from getting swimmy headed and passing out from high CO. So you want that CO detector, generally up closer to your face when you're doing some of these tests. Now, when we're looking at ovens, you can see there's this nice little animation we found. Ovens are designed to operate with the door closed, right? Air comes in the bottom and exhaust comes out of that little exhaust port. The exhaust port's pretty skinny, so some exhaust air is going to come out, but not a whole lot. But for every bit that leaks, goes out that exhaust, fresh, air is coming into the bottom. If we open up the door, then you increase that flow of air, you decrease the temperature, and even though you're getting more air, the decreased temperature, it really kills you with the CO production, right? For CO to go into to react to CO2, it needs to stay within that gas flame air reaction, and a higher temperature gives you results in CO2 rather than CO. So opening the oven is actually going to create more CO. So again, I encourage people to leave that oven door closed as much as possible. And for those folks that try to heat their place with the oven door open, the clock's ticking on them. Darwin's going to put another notch on his belt. All right, so here's a graph that we had when we measured CO. So the blue lines are the temperature. So you can see it starts out low, temperature rises, and it kind of plateaus over time, right? The CO starts out low, peaks at startup, and then drops down and kind of also plateaus low typically once it's warmed up. The BPI standards want us to measure at steady state, so that's usually between 5 and 10 minutes. And that's what we report for folks, but I always take a note of this high CO because this is when people usually kind of fiddle around with their oven. They start the oven and then they say, oh, I need to adjust before it gets warm, I'll adjust the shelf. And oh, there's a dirty spot, let me clean up that spot. So while this thing is at its highest CO production point in production, they've got the oven door open because they're diddling around with things. That's the most critical time to have that door closed, is during that warm up stage. So here's an oven that we tested, and you can see, in the little graph there, at minute 15, we had 2,200 parts per million of carbon monoxide outputting. Then at steady state, it got down to 140, right? 225 is what the gamma standard is for carbon monoxide output on an oven. I still think that's too high, but we'd fail every oven if you had it much higher than that, or you get any higher. So 140 parts per million of carbon monoxide at 10 minutes is actually passing, but at 2,200 parts per million at startup, that's dramatic, right? And so those are things that we look out for. And if you just had your little rattler carbon monoxide detector and you put it at that outlet, you might not read 2,200, but you'd know that it was over 1,000. You're going to get some dilution with that little guy because you're not putting a probe right into the exhaust port. But even that little guy will read into the hundreds of thousands. It'll scream, it'll flash, it'll vibrate. It's basically trying to save your life. You can do this with a carbon combustion analyzer, or you can get a pretty decent idea of what neighborhood you're in with just one of those personal carbon monoxide detectors. Ovens are typically the highest CO source in homes. This last couple days, I've had a couple of ventless gas fireplaces, and the ventless gas fireplaces were putting out less carbon monoxide than the ovens. I can't make sense of it. You'd think that the fireplaces would be worse, but they're actually dialed in and burning cleaner than the ovens. So go figure. Bottom line, I'm going to say with gas oven testing is I encourage homeowners to use the range hood that exhausts to the outside all the time, whether they use the stove or the oven or both. You will need to get those particulates and those exhaust gases gathered up and out of the house. The recyclers don't do well. And I generally encourage people, if they're going to be doing any kind of renovations or anything, or if they have indoor air quality concerns or respiratory concerns, to get a range hood that exhausts to the outside and use it all the time. All right. I'm going to move over to water heaters, furnaces. So generally these kind of fall into a couple different classes. We've got the atmospherically vented class. These are units where the exhaust byproducts are being carried out by the buoyancy of their own heat, right? So the most basic kind is the natural draft. Almost every water heater, like you can kind of see at the bottom right there, is a natural draft water heater. If you see that little draft hood on there, again, the hot exhaust gases are carrying themselves out by buoyancy. The upper graphic there is kind of a graphic version of a natural draft furnace. Natural draft furnace is going to have a big open draft diverter opening right at the front of it. Both of these are going to use metal exhaust pipes, so either single wall or double wall exhaust line, vent connectors. There you go. And those vent connectors will eventually connect to either a masonry flue or a B-vent flue, going up through the house and ultimately to outside. These are exclusively using inside air for combustion. So they need air from whatever room they're in for combustion. So if you have natural draft appliances, make sure, take a look around and see if there's enough space, enough volume of air around there for combustion. So these we mentioned hot gases rise due to greater buoyancy. The open draft hood is for dilution air. Spillage is possible at that draft hood. So we want to look around the draft hood to see if there's any signs that exhaust is spilling backwards. That exhaust is going to be hot, moist, and acidic. So it's going to rust things, right? It's going to corrode the top of the enamel top of the water heaters. It'll start to corrode pipes. It'll melt plastic. So it becomes pretty obvious if you've got, occasional persistent exhaust spillage is generally easy to see. There's always signs. Occasional exhaust spillage will even show some signs there. We'll talk about those. The other types of atmospherically vented furnaces are induced draft or mechanically assisted furnaces, all right? So these are our 80% furnaces that we see. It's going to have that little inducer fan up at the top. It also uses metal exhaust pipe as the vent connectors, uses inside air for combustion. Again, hot exhaust gases rise due to greater buoyancy, although these gases are somewhat usually in the range of 325 to 375, right? So cooler, but not cold, still hot enough to carry themselves out. Then the natural draft units, those can be anywhere from 400 to, I've seen 770 degrees on a 50-gallon water heater. It was exhausting over 700 degrees of exhaust heat, making 120-degree water. So I don't even want to know what the combustion efficiency on that one was, but it's horrendous. These inducer fans pull combustion air through the heat exchanger. So the air comes in, it gets sucked in along the in-shot burners through the meandering heat exchangers, because the heat exchangers are not just straight plates, they kind of zigzag back and forth, more like a maze. And the fans pull the air, the combustion air through that maze, right? The fan does not push exhaust up and out. If I drilled a hole into the flue right above the furnace, that hole would suck more air in, right? The pressure goes from positive at the outlet of that fan to negative because of the draft pressure, the buoyancy of those hot gases within inches, right? And we've demonstrated this at a combustion lab near here, and I get HVAC guys that don't believe it until they see it, right? They believe that those fans push the exhaust out, and they do not. So it's still the hot gases carrying themselves out. The fan is just there to pull combustion air through the heat exchanger. All right. So image on the left, you can see kind of the open top of one. This one's got 5 heat exchangers, 5 burners. You can see the 5 plates above the fan, and that fan is sucking on all 5 of those heat exchangers to pull air in through the burners, through the manual heat exchanger, and then up the flue. All right. How do we measure CO in these guys? Again, this starts to get a bit invasive. I would say generally more invasive than we will get during a typical home inspection. Again, if you have a combustion analyzer, because you do more advanced combustion testing or for whatever reason, the image on the left, I could take a probe and probably get it up under that hood and get it down into the exhaust portion of the water heater. Even the center image, which is a natural draft furnace, I could probably get the probe into the draft diverter opening and get it into the oval exhaust opening of the heat exchanger. That graphic shows 4 burners. There would be 4 of those heat exchanger openings. So if I were to measure CO on that unit, I'd want to put my probe into each one of those heat exchangers to see what each one's doing. And again, out of direct experience, I can tell you that one of those 4, 5, 3, however many burners you have, there's always going to be one that's going to be bad or worse than the others. And it's usually the one with the standing pilot. So the standing pilot results in a lot of debris. There's not very big openings in those heat exchangers to kind of slow those gases down so that you get good heat exchange. And as those little gaps and openings clog up with particulate, it throws off the whole fuel and air mix, and you'll start seeing usually one of those heat exchangers starts looking really bad. You'll see the ribbon burners are getting dirty and yellow. You might start seeing soot, and when they're really bad, you'll get flame rollout because that fire wants oxygen, and it will roll right out of that combustion chamber and come right back out in order to gulp air. It's pretty crazy, but it won't be all 4 of them. Typically, it'll be just the one that's clogged up the worst. On the right-hand side, we have our induced draft furnace. So to measure CO on these, we're typically just poking a hole in the vent connector right above the fan and measuring it there. Obviously, any holes that we put in any of these vent connectors, we're patching them up. We're usually putting metal tape on there. Generally, that's all you really need to do. If the tape is starting to get old and crusty, then take it off, put a new piece on for folks. Carry on. Proper atmospheric venting. So these are the vent connectors coming off of water heaters, furnaces. Generally want to see a 1/4 inch rise per 1 foot of horizontal. So if I've got a horizontal portion, for every foot it goes laterally, I need to see at least a 1/4 inch rise on that. So I'll take a tape measure. I'll measure, say, here's a 2-foot section. I'll often measure from the ceiling down, because usually the ceiling is level, the floors might not be. And I just want to make sure that, however many feet, I multiply, by a 1/4 inch, and on a 2-foot pipe, I want to see a 1/2 inch of rise, at least. The minimum vertical rise is, what we're talking about here is how much straight pipe should I have coming off the top of a water heater before I throw an elbow on it. The convention is 3 times the vent diameter. If I've got a 3-inch vent connector, I want to go 9 inches up before I throw an elbow on it. 4-inch diameter, I want to go 12 inches before I put an elbow on it. It's a convention. We've seen them work with smaller vertical rises, but all things being equal, and if you have the ability to do it, you'd want to see some vertical rise off of those before throwing an elbow. And the elbows create a little bit of flow resistance, and it can lead to spillage. So we want to minimize the spillage, so we want to give it a nice running start before we throw an elbow in the mix.
Hey, Joe.
Yes, sir.
What's the purpose of measuring the CO inside an appliance or a vent pipe?
If the CO is outside the standards, and I've got a slide here that mentions what those are, then we know the combustion process is off. Again, this starts to get a little bit into the weeds, but generally speaking, if I'm measuring the CO, say on an 80% furnace, and I'm watching it gets into the 20s, 30s, 40s. When I start it up, when that blower kicks on after 30 seconds or 45 seconds, after the heat exchanger is warmed up, if my CO goes wonky on me, if I all of a sudden I go up to 200 or 300 parts per million, then there's evidence that with the addition of the blower across my heat exchangers, it threw my fuel air mix off and made my CO go crazy. That's evidence that there's a crack in the heat exchanger somewhere. Air is either getting pushed in or sucked out of that heat exchanger and thrown off the combustion process, resulting in high CO. In some cases, it's just, again, ultimately we're looking for malfunctioning equipment, right? If I have a cracked heat exchanger, equipment's malfunctioning, it's damaged, not working properly. In some cases, the gas pressure is too high. It's going to beat up, the equipment's going to beat up, there's going to be unburned gases, it's going to be more particulate. So you're going to see shorter life, poor efficiency. And if you have something like a cracked heat exchanger, now some of that CO could be getting into the conditioned air stream. So again, I will admit, this starts getting into the weeds. I don't do this on a typical home inspection, right? But sometimes we do investigations for folks that go beyond the typical home inspection. So these are some of the lessons that we've learned. And sometimes your spidey sense tingles and you go, I'd like to look a little further. And so that's the short.
Quick follow-up. A quick follow-up to that. Sorry. What's a typical reading after 5 minutes in an 80% unit?
Generally, we want to see below 50. I think below 25 is outstanding. If you can get below 25 parts per million, that thing's whispered, like dialed in. You got good fuel air mix on that. Obviously, the higher it gets, the more concerning we are. And I believe on furnaces, it's 400. Again, we start to get into the little weeds here. The gamma standards talk about CO air free, which is another little calculation that gets done to figure out what kind of CO is being produced at the burner itself. And so those readings have to be below 400 parts per million CO air free. The actual CO reading might only be 200 or something in that range, but the CO air free is actually the pass-fail standard that we have to measure to. So that's for advanced combustion safety. But generally speaking, we want to see CO as measured. So just stick a probe in the stream. You want to see levels that are below 100, ideally below 50 or 25. All right.
Thank you.
You bet. All right. I think some of this is fairly obvious to folks. Those of us that have inspected homes for a while. The vent connectors need to increase as others join. If I've got a 3-inch coming off a water heater and a 4-inch coming off a furnace, then the two together should be bigger than a 4-inch, right? Now you're gonna have to look at a schedule there to, a vent connector schedule to see like, okay, if I take a 4 and a 6, put them together, what do I need to output? Generally speaking, you can look at it and go, what sizes are they? Are they increasing as I add appliances to them, right? That's a very common thing is that they won't increase in diameter. And so it's something to look out for. The other thing with commonly vented units is typically you want to see the smaller BTU unit venting above the larger BTU unit. So the furnace is our large BTU appliance in most homes. It's running long cycles, periodically throughout the hour. It creates a flow of gas up the flue, right? The little water heater that kicks on every couple hours can piggyback on that stream of exhaust air, right? If it comes in below, it has a harder time establishing its own draft. Typically, Y fittings assist in the natural upward draft, so Y kind of pointing the exhaust in the direction you want it to go. If you're connected with T fittings, you're presuming that the exhaust gases know whether to take a left or a right. And I wouldn't make that presumption. And I'd be looking for, possibility of exhaust spillage. And then the smaller units typically Y into the larger unit for that same reason above. The Y is the branch coming in. The straight part of a Y fitting, it would be your high BTU appliance, kind of establishing that draft. So,
hey Joe.
Yes, sir.
Is that a code requirement that the smaller one goes above?
I'm going to have to say I don't know. And part of the challenge is like when we do the BPI standards, and it's spelled out in the BPI standards as well, you know, for us to look for this. But I can tell you that, you know, in some cases you're looking at it or we're testing and you say, hey, everything else is working fine, except for the fact that the big one ties, you know, tees into the little one, you know, so they got the order kind of swapped, but nothing's spilling, everything's working, you know. So at some point you have to kind of go, well, maybe it's not following the letter of the law. I'm going to still bring it to your attention. So if anybody does any work, they can reconfigure this to make it proper. But it's working in the meantime. In some cases, it's not working, and so part of the reason why it's not working is because it's not configured properly. So we need to reconfigure it. So if the only thing that's wrong is that, you know, the bigger one tees into the smaller one, but everything else is working, there's no signs of spillage or anything like that. Again, I'd make a mention of it, but I wouldn't make a big hairy deal out of it. So sometimes. Usually there's a lot more, you know, a lot of other things to be focusing on rather than some of these, you know, smaller details. So again, something to be aware of, something to keep an eye out for, and you know, it might alert you to other not, you know, less than professional work, right? All right, continuing on, improper venting. These can include blocked or partially blocked chimneys, vents or vent connectors. It can include no chimney liner for orphan water heaters. So an orphan water heater is a water heater that used to share a flue with a furnace. That furnace has been removed, and now we've got this little water heater all by itself. That chimney flue needs to be reduced so that the smaller BTU water heater can establish its draft. You're looking for a corrugated liner coming out of a masonry chimney typically. That's usually the ones that need to be lined, and we're looking for, like I said, corrugated liner coming out at the bottom. We have improperly designed vent systems that have indirect routes, negative slopes, or T-fittings. Keep in mind, clearance to combustibles. Single wall needs 6 inches of clearance. B vents need 1 inch of clearance to combustibles. And then again, if you know that something is not the code, I'm not saying use code, it's not the code language, but still bring those items up saying, hey, this is not done to you know, professional standards or best practices. Here's some examples of, I don't know what they had on the shelf here, but clearly they were trying to get around something. Each one of those elbows is like the equivalent of 10 feet of resistance. So you get an extra 40 feet of resistance on this thing. So it's going to end. We don't have a very high vertical rise off of that water heater. So this guy's going to be prone to spillage. Don't even ask me what's going on here. There's no good reason why this thing could not have had an upward slope. They very easily could have cut down that vertical rise on that water heater. I mean, they already cut the little tabs on it. So that one should have an upward slope, not a downward slope. Here we have a commonly vented unit where you've got an induced draft furnace on the right. Again, you got this nice big column of hot gases going up. It should, you got a T back to back with a Y fitting. And so sometimes just the velocity of that airflow can push back down and spill out on the water heater. So it's not that the water heater is spilling, it's that the furnace could be pushing out gases at the water heater. So this would be an issue where maybe both of them have to be reducted or vented outside. Vented properly. When we have condensation in the vent connectors, that means the exhaust gases are cooling down, the moisture is condensing, and that acidic condensate is then eating up the joints. So solutions to this could be, taking all the single wall out of there and replacing it with double wall vent connectors. So I don't even know what is going on here. Here's a concentric vent for a tankless water heater. Get her done, man, apparently. So this is wrong. That thing should be independently vented to the outside. It shouldn't be tying in with anything else. This one looks a little crazy, but that's stainless steel vent connector. It's flexible because they had to get around this furnace filter. This is a downflow furnace. The furnace filter is right in that plenum, so they had to get around it. So they used stainless steel. Now the water heater, I don't know, I probably would have swung that Y around, have that Y kind of come off this way and make a little shorter trip. So, but sometimes, as crazy as this looks, it works. Nothing spills, and you're good to go. So you'd say, hey, this is atypical solution. It's working, but there's some room for improvement here. Flame rollout. I don't know how many people are seeing flame rollout much. I haven't seen an active flame rollout issue in quite some time. Usually, like I said, it's because of a clogged heat exchanger. Last time I've seen them. So typically an obstructed heat exchanger. Sometimes it's because there's no draft diverter on top and you're getting bad draft air coming down. But again, in my experience, typically they're obstructed heat exchanger issues. And again, as we get more sealed combustion units, we're not going to see many of these flame rollout issues anymore. But if you see it, obviously we're writing it up. All right, other types of exhaust. We have power vented units that are one PVC pipe. They use inside air for combustion, and the cool exhaust air is pushed out by the black fan you see on top of the one on the left. The direct vent appliances are two PVC pipes, also known as sealed combustion. It uses outside air for combustion, and then the cool air is pushed to the outside. Both of these are category 4 appliances. The one is using inside air for combustion, the other one is using outside air for combustion. So yeah. For these guys, we're generally, if you wanted to measure the carbon monoxide output on these to see, how if everything is still functioning properly, you would just go measure it at the termination outside. All right, so here, this power vent, or we have a direct vent unit on the right here. So our intake pipe comes in at the center, goes to where our burner assembly is. Then our inducer fan is our draft inducer fan is all the way at the bottom. So it's pulling the flame and combustion gases down through the unit. And then it pushes it up through the black pipe and up and out on the right-hand side. There's your direct vent unit, sealed combustion. Then we've got this crazy little unit here. Two things about this one, or a couple things. One is it's only sealed combustion when the door is closed, right? Those burners are open. So if that the cover is not put on the cabinet, that is not a direct vent unit. Also, if the pipe, the air intake pipe, is not piped into the top of that thing, then it is not a sealed combustion unit. It can still be a high efficiency furnace, but you would have to say it was configured as a power vent unit, but it's not sealed combustion. One, the door is missing. Two, I don't have an intake pipe. And then the fact that the PVC pipe is duct taped, I'm flagging this whole thing, right? I mean, this is, not professionally installed. You're disclaiming the whole thing. That the thing was a train wreck. But this kind of configuration is pretty typical, where you've got high efficiency furnace, could be set up as a direct vent or sealed combustion setup, but they left the intake open, and you can draw debris and such into the unit. We had one in a hair salon, and the chemicals from colorant and perm, doing hair perms and stuff like that, actually started eating up the heat exchanger as it got drawn into the unit. So generally, ideally, a manufacturer wants these things piped all the way to the outside. And check the fittings. Make sure everything's glued. I can't tell you how many times I've come across these where the pipes were just dry fit and nothing was glued. And check the outside terminations. In the wintertime, this is not too difficult. You're going to look at it. I should see exhaust coming out of that one that's snorkeled up, because the exhaust is warm. It's going to rise up and away. The lower one should be for intake. In this case, they were flipped around. So doesn't happen often, but it's not all that rare. They do often kind of, maybe the guy's looking at it from the inside, exhaust is on the left, intake's on the right, and then he goes outside, changes his orientation, exhaust is on the left, intake's on the right, and he swaps them around backwards. So make sure that it's exhausting out high and intaking down low. All right. Another quick tip. This is what we do on. I do this on just about every home inspection. I'm looking at temporize on a furnace. Again, this is not a combustion safety thing. This is a furnace performance thing, and manufacturers are pretty clear on this. If it's not operating within these ranges, so our high cycle is says that the heat rise needs to be between 45 and 75 degrees of temperature rise. On low, it's 50 to 80. So if it's above that, then it's out of spec. Something's wrong. There's a restriction in the system, and it could void the warranty on that. So it's not operating as intended, and I need to have a qualified technician come out and evaluate further and correct as necessary. On these guys, I'm measuring the return temperature just before it goes through the filter, and I'm measuring the supply air as it gets past the heat exchanger and AC coil, so well above the AC coil. For this, you need 2 thermometers. You're checking it at steady state. Again, higher temperature or lower temperature is bad. It's got to be within that range. And as you're doing this, we've noticed, and I always wonder how many of these I was missing. As I'm monitoring it for temperature. I mean, I'm inspecting other things at the same time, but if I hear the furnace clip off, I go over there and see, like, hey, I turned the thermostat up 10 degrees. I know it didn't satisfy my thermostat. How come this thing is shutting off after 6 minutes? Okay, it turns back on after 3 minutes, it cooled off, and it runs for another 6 minutes and shuts off. That thing is bumping up against the high limit, right? You have every reason to write that up. It's not operating as intended, and you can get a HVAC contractor to come out there and give the furnace a once over. Figure out what's going on there. Well, our time is getting short here, but I want to talk about house pressures. So we have a little push and pull with house pressures. Stack effect is the upward flow of air in a house due to temperature difference between inside and outside. Warm, humid air is exfiltrating out the top. Cold draft air comes in at the bottom. If we have a strong enough stack effect, it can actually pull air down the flue of a water heater and into a house. This is generally in the shoulder season when the furnace is not going, but I've seen some pretty strong stack effects, pull some air down. We also have wind. This is, if the chimney's on the windward side, that positive pressure can push down the chimney and cause spillage at the water heater. I've actually had 80% furnaces that the pressure switch on the inducer fan was weak, and that wind pressure pushing back on it caused the pressure switch to trip, and the furnace kept shutting down. This is not it's not atypical. I mean, it happens when we have really strong winds. And then we have mechanical fans. This is probably the most common, where we have this tug of war of exhaust appliances, the range hood, bath fans, dryers, all sucking air, pushing them out of the house. And in our now tighter homes, as homes have gotten air sealed and insulated for weatherization and comfort, we have fewer holes, and the vents above the furnace and water heater can let that air in and spill backwards onto the water heaters and furnaces. So this is kind of an interesting dynamic. If we have leaky ducts, okay? If I've got ducts that, in this graphic, obviously it's very simplified. I've got supply ducts going through a unconditioned crawl space. I've got returns going through an unconditioned attic. If I've got supply leaks in that crawl space, then I'm not going to get all my supply air into the home. The return is still going to want to pull an equal amount of air, and I'm going to end up with a negative pressure in the house. So the leaky supplies are acting like an exhaust fan, giving me a negative pressure in the house. Conversely, if I have return leaks, the returns are going to suck air into my system, and so it's going to have the net effect of pressurizing my house. This dynamic can be seen along with measuring the temperature on your supply and return. In the summertime, if my return air is warmer than my thermostat's 73 degrees, but I got 83 degree air coming in across my furnace filter, how's that air getting warm? It must be sucking in hot attic air by way of the return ducts, bringing that into the system and raising the temperature of my return air before it goes through my air conditioner. So now you've proven that you've got duct leaks connected to the attic by way of the temperature measurement you took on the ductwork there. Now we have room imbalances. Commonly, we have bedrooms that have supplies. There's no return. When the door gets closed, the room pressurizes. The part of the house that has the main return, that has a negative pressure. So we have exfiltration in the bedroom. We have infiltration in the other areas. So we start seeing weird pressures being generated by that. Obviously, our ideal scenario would be the supplies and the returns delivering and drawing away equal amounts of air, and that's only possible when we don't have any kind of duct leakage. So here's a grill that somebody cut in the return. This guy was, it's 18 inches away from the blower. This thing was depressurizing the combustion appliance zone around there and causing the water heater to spill exhaust. These guys, same thing, open filter slots in a rather constrained room. Every time these guys kick on, these are acting like an exhaust fan. They're sucking air from the combustion room, drawing it into the ducts, and effectively acting like an exhaust fan, and can cause water heater spillage. That water heater is counting on the negative draft pressure to be stronger than the CAS pressures, the combustion appliance zone pressures around there, right? But if I've got a lot of suction sources, exhaust fans, dryers, open filter slots, return ducts that have big gaps in them, right? I can have enough negative pressure where the water heater loses this tug of war, right? And water heaters have a pretty low depressurization limit. They cannot withstand a lot of negative pressure in the opposite direction. So when we do these testing, we're looking for, what are those pressures? What's playing tug of war with it? When we're looking for occasional spillage, you're looking for these little melted grommets, right? So the grommets around the hot and cold water, if you see them kind of warped, right, that's telling me that I got some occasional exhaust spillage. It's melting that plastic. This can be a large exhaust fan. Maybe it's a whole house fan that somebody turned down without opening enough windows. It could be wind down the chimney. It could be room pressures like we talked about. Maybe there's a dryer in this room and somebody closed the door, and that negative pressure from the dryer causes the water heater to spill. It could be fluid geometry. It could be fluid obstructions. Either way, I'm not calling the plumber out to do this, because the plumber is going to hook it up the way the manufacturer said it was to be hooked up, but he has no idea what house pressures might be affecting this, or what wind pressures. If you have exhaust spillage, the next step would have a BPI building analyst come out and do it. It could be an HVAC contractor, it could be a third-party building analyst, but somebody who knows how to do a combustion safety evaluation, looking for the pressures and obstructions and the whole array of issues that could be occurring here. Persistent exhaust spillage, I mean, you look at that thing's spilling all the time. Those hot acidic exhaust gases are melting that nice flower pattern onto the top of the water heater, and this is likely from a clogged flue or very strong forced air unit pressures, by the open returns or big duct leaks. It could be constant exhaust fans that are drawing air out of the house, or big range hoods, and it could be in conjunction with a very tight house, right? So the tighter the house is, the more those fans are going to play tug of war, and unfortunately that water heater flue is just a nice convenient opening for relief air. All right. Again, to figure out, to really get to the core of this issue, somebody's got to, a building analyst's got to do a full combustion test to figure out exactly what dynamics are occurring here. Again, the goal of a worst case depressurization test, which is the scenario of testing that we do to figure this out, is to make the appliance fail. If I can do it on purpose, the homeowner may be doing it by accident and not realizing it. So how much pressure is too much? Oh, by the way, this is way behind the SOP. So again, a lot of this is, for me, this was to satisfy my curiosity as a property owner. And then we started doing it for other folks that own properties that had issues. But here you can kind of see a graph where we measured pressures in this combustion appliance zone. We started out at 2.1, you can see on the right. And as we turned on the exhaust fans, the pressure went more negative. We turned on the dryer near the combustion appliance zone, it went more negative. The air handler made it go a little bit more. Door closures made it go a little bit more. Effectively, we went beyond what the limit was on this configuration of appliances. And so we can see that, what set of appliances had what effect. And sometimes we can make some changes easily. Sometimes, the answer is to simply upgrade the natural draft appliance that is inefficient and prone to spillage with a higher efficiency unit that is also safer. And safe is easy to sell to people. Hey, get the natural draft or the power vent water heater or the direct vent tankless water heater because they're safer. Oh, and they're more efficient. So, but when we're testing for spillage, we're generally puffing smoke there, and this video kind of shows it. Sometimes it's drawn in, sometimes the smoke is pulling back out. We're able to kind of fiddle and create an obstruction in this, so you can kind of see how the smoke spills back at us here, and then at other points it draws up into it as we open up the restriction. So there's our CO at steady state. For a water heater, it's got to be less than 200 parts per million CO air free. For furnaces, under 400. Sorry, we're going to keep plugging through. We're almost at the end here. Dryer safety. All right, this one is fairly common. People installing vinyl or metallized mylar exhaust ducting with gas dryers. First of all, they've got a lot more little ribs and humps and stuff in there that can catch a lot of lint. Gas dryers get hot. If the lint in the dryer starts on fire, that lint will just keep burning through there and eventually burn right through the exhaust ducting on there. So on gas dryers, especially, we want to install metal ducting. This could be flexible metal or solid metal, but it's got to be metal. All right. And you see, like on the very right-hand side, you see a corrugated aluminum duct that works fine. If they're changing those out, we still want to recommend that they clean the entire line of lint and just make sure there's nothing left behind if they're going to be swapping that out. There is no CO testing criteria or procedure for these guys. So really it's just down to kind of fire safety. Make sure there's no gas leaks on these, and then make sure that the vent line is clear of lint and is metal of some sort if it's the gas dryer. All right, so wrap this all up. Here's what issues to look for. And I've got these kind of like, this is, again, in my experience, what I see most common. The dryer exhaust duct material. Very, very common that they're using that metallized mylar, which is basically just a metal deposition on plastic. Just spring steel with plastic around it. It'll burn right through in no time. So a good dryer vent cleaning is cheap insurance. Looking for gas leaks in homes. Again, it was more prevalent in my neck of the woods in the past. The prevalence is going down, but we're still looking for gas leaks because we still find them. And people become symptomatic because of low level. Again, we're not talking about explosive gas leaks. We're talking about the ones that are low level that you wouldn't necessarily smell with your nose unless you put your nose right up to the fitting. But it's enough to get people reacting to it negatively. We want to check out oven CO and range hood venting. Again, you can presume that most ovens put out high levels of CO because the vast majority of them do. The ones that put out the lowest CO are unfortunately like the $3,000 Viking, Wolf, and Blue Star ranges. It's nonsense that somebody has to spend thousands of dollars on a stove to get low CO. But those are the lowest ones I've seen. Those are, pretty regularly in low double digits of CO output. And I've seen new ones test out at 600 parts per million once warmed up. So it's bad. Generally, again, whether the CO is low or high, I always want to take all the exhaust gases and exhaust it to the outside. So I want to have range hood venting to the outside above all gas stoves. Combustion air requirements, and again, measure those guys. Look for your furnace temp rise. Again, I know the furnace temp rise is not a safety thing. I guess it could be if it keeps bumping up against its high limit switch. At some point, that high limit switch is going to fail, and then you're going to have a runaway combustion. So check furnace temp rise. It's you can't have a technician is going to have a hard time arguing that it's okay for the thing to run 15 degrees warmer than the manufacturer says it should. Then look for melted grommets on the water heaters or any other kind of corrosion over your water heater for signs of exhaust spillage. Look for corrosion near draft hoods, whether they be water heaters or natural gas furnaces or even natural gas boilers for that matter. And obviously, if you have evidence of a flame rollout, obviously then you got to throw up the big warning sign on that one. But again, those are fairly rare. I think I've only, in the last 10 years, I think I've come across 2. So, all right. Benefits of CO testing: you will detect dangerous levels of CO, a malfunctioning unit, inefficient units, or potentially a cracked heat exchanger. And if there is a cracked heat exchanger on a unit, your homeowner or the home buyer is going to really appreciate you finding that out before they own it. And of course, you're going to recommend further analysis and repair by a qualified HVAC technician or DPI building analyst if you've got spillage issues. Benefits of combustion safety testing basics. Make sure you're looking out for these dryer vent material, gas leaks, and high oven CO. Keep an eye out for exhaust venting issues, malfunctioning equipment, and hopefully you guys got a better understanding of how some of these house pressures can affect combustion exhaust flow. It's not always a clogged flue. In fact, in my experience, it's very rarely, obstructed flue. I'd say maybe 10% of the time. The other 80, 90% of the time, it's because other fans, other equipment is playing tug of war and the water heater is losing. So, all right, any questions?
Yeah. Is any information about proper ASTM rating for combustion ventilation on PVC? Damn, Jim.
140 degrees is the number that's coming to mind. If anybody can correct me on that, but I believe it should be under 140 degrees. Again, my experience with anything power vented or direct vented, as we go measure CO outside with our combustion analyzer, it has temperature reading on it as well. Yeah, if it gets above 140 degrees, then the PVC starts to get a little pushy. So it should generally, they're running between like 90 and 120 degrees.
Thanks. How often do you recommend people clean their dryer vent?
Once a year. And I will call it out for like homeowners associations, like condo buildings and stuff like that. It's hard for any of those folks to do them, onesies, twosies. And it's something that I've had clients bring up to the condo board to say, hey, we should coordinate this. It's a safety issue. If somebody has a fire, it affects everybody here. And it's going to be more cost effective for us to hire one company to come in and clean all the dryer vents on one day. And they typically go to the roof or wherever the terminations are, and they generally do them from the outside. So.
Gotcha. Natural gas ranges are not required to be vented, correct?
They are in Illinois. I don't know. They should be vented. I mean, obviously, well, they're an unvented appliance by their nature. They're an unvented appliance designed to exhaust into the home. But I think the code is a little bit behind here. The PM 2.5, the low particulate that comes off of cooking is very, very dangerous to respiratory health. And the biggest source in people's homes is cooking. There's all kinds of little particulate, little droplets of oil and stuff like that come off of food as you're cooking that get up in the air. So you want a range hood to gather all that stuff up and get it up out of the house. We've had issues with builders where they'll put in a range hood, but it doesn't exhaust to the outside. It's just a recycler, right? And those grease filters, I don't know. That's just a lie that people tell themselves. It doesn't do anything to reduce the exhaust gases. It doesn't do anything to reduce the only particulate that gets stopped is whatever gets stuck to the grease screen. But the holes in those grease screen are way too big to effectively stop PM 2.5. So there's a lot of good reasons to vent them out to the outside.